Okay, in the last video we saw that one way to solve a system of equations is to graph the two equations as lines and find out their point of intersection. Here we have three various examples of systems of equations. In this first one we can see that they are both written in general equation of a straight line form, ax plus by plus c equals 0. And we can see that we could also write the first one as 7y equals 42 minus 3x, so y equals 6 minus 3/7x, which is of course a straight line. And similarly the second one, here we have minus 3y, so let's make that one positive, so move that one over to the other side, so 2x plus 12 equals 3y, so y is then 2/3 x plus 4. So we have two lines and we can find out their point of intersection. A very quick sketch will tell us that the first line has a y-intercept of 6 and a slope of minus 3/7, and the second line has a y-intercept of 4 and a slope of 2/3, and where they intersect are the x and y values for the solution. The second one, similarly, we're not using x and y, but it's easy to see that we could replace a by x and b by y or something similar. This is nearly the general equation of a straight line, and we can see particularly from the second one that there are nice solutions to this. To find the intercepts, if a equals 0, then we're left with 5b equals 45, so b equals 9, so we have 0, 9, and if b equals 0, then 7a would equal 45, so a is 6 3/7. So again 6 3/7, 0, and we can use it to plot the line, and similarly for the other one. This third one actually is probably best solved by something called substitution, because in the second equation we can write q equals 8 minus p and then substitute that back into the first equation. Really, my purpose of doing this is just to explain that all of these systems do have solutions which could be graphed, but there are other ways to solve them. However, before we get to solving them, we first need to figure out how do we end up with systems of equations like this. So we're going to look at a few examples of word problems where we're asked to construct a system of equations to model them, and we'll look at some solutions of how to do this in a kind of seat of your pants way before we get on to proper methods of solving. So please pause the video and make sure you understand what the question is asking. Okay, well, in the first condition we have 5 burgers and 4 fries and the bill came to 26, so it's easy to think that we could write this as 5 burgers plus 4 fries equals 26, and in the second bit of information 2 burgers and 6 fries equals 17. But what does B and F actually stand for? Does B represent burgers or the number of burgers? Well, no, because we know that there were 5 burgers and we know that there were 2 burgers. So B doesn't represent the number of burgers. These questions are both talking about the total cost. So in fact, B represents the cost of one burger, and similarly F represents the cost of one portion of fries. So 5 burgers each costing B dollars plus 4 fries each costing F dollars comes to $26. So B is the cost of a burger and F is the cost of a portion of fries. Okay, now the interesting thing about solving this is that both of these expressions 1 and 2 are independently true. So if Bert instead hadn't bought 5 burgers and 4 fries, what if instead he doubled that order and bought 10 burgers and 8 fries, well, it would have cost him twice as much. So that would have been $52. Similarly, if Ernie hadn't bought 2 burgers and 6 fries, what if he'd done 5 times that much? Well, he'd have bought 10 burgers and 30 fries, and 5 times 17 is $85. So we can see from these two that they both have 10 burgers, but Ernie's order has a lot more fries than Bert's order, and that difference of the fries is causing a difference in the cost because they both had the same number of burgers. So realistically, what's happened is that Ernie's bigger order, which is 30 fries, now has 22 fries more than Bert's order, and that is causing a difference in cost of $33. So the fact that Ernie had 22 portions of fries more than Bert has caused a difference in cost of $33. So if 22 fries cost $33, then 1 fry costs 33 divided by 22, which is $1.50. So if the fries cost $1.50, we can use that information and say, well, if 1 fry is $1.50, then 4 fries would be 4 times $1.50, which is $6. So if 5 burgers and 4 fries is $26, the 5 burgers must have been $20, and so the burgers are $4 each. We've answered this question really by a common sense method of comparing the two orders and scaling them up. The proper name for this is elimination, and we'll come to that in the next video. So here we have a second typical example. Please pause the video and read it carefully and make sure you understand it. So the question is really asking for how many students and presumably how many teachers went on the trip. We know what the cost of the tickets were, but we don't know how many students there were and how many teachers there were. Let S equal the number of students, and let T equal the number of teachers. So altogether they buy 40 tickets. In other words, there's 40 people. So the number of students plus the number of teachers must equal 40. The other piece of information is the cost. So how do we get the total cost? Well, it's the number of students times by the cost per student, and the number of teachers times by the cost per teachers. So if there were 2 students, the student tickets would cost them $16. If there were 10 students, the student tickets would cost them $80. If there were S students, the ticket cost for the students would be 8S, and equally the cost for the teachers would be 11 times by the number of teachers, and altogether that comes to $338. So here is our system of equations. S plus T equals 40, 8S plus 11T is 338. We could use a similar approach then to example 1 and scale up the first equation and multiply it throughout by 8 and say that suppose everyone paid $8 for the tickets. 8S plus 8T would equal 8 times 40, which is 320. However, we have 8S plus 11T equals 338. The difference in these two is clearly the second one has 3T more, and it is causing a difference in cost of $18. So T must equal 18 divided by 3, which is 6. In other words, the number of teachers is 6. And altogether, if there were 40 people, then the number of students must equal 34. So the answer is 34. An alternative way to do it is to do something called substitution. If S plus T equals 40, then T must be 40 minus S. The number of teachers is 40 minus the number of students, since altogether there are 40 of them. And we can use that fact and substitute it into the second equation. So 8S plus 11T, but T is just 40 minus S, equals 338. So what we have here is 8s plus 440 minus 11s is 338. So minus 3s equals 338 minus 440, which is minus 102. So s is minus 102 divided by minus 3, which is 34. This is a little more algebraic, but it also gives the right answer. That is called the method of substitution, which is probably the most sensible one in this case. This final example has appeared in sample exams in the past and is really about speed and travel. So please pause the video, read it carefully. We're talking about speed, time and distance, and you should remember from physics and early maths that distance equals speed times time, and we have a journey of 600 is equal to outbound speed times 5 hours, and equally 600 equals return speed times 3 hours. But what are the outbound and return speeds? So on the outbound journey, the plane is travelling with a forward speed of v against a headwind of w. Therefore, its speed over the ground is actually being slowed down by the headwind. So its speed over the ground is v minus w. Whereas on its return journey, it is flying at a speed of v, and it is being pushed by the tailwind of w. Therefore, its effective speed over the ground is v plus w. So the outbound speed was v minus w, and the return speed was v plus w. Obviously, if 5 times v minus w is 600, then that means that v minus w must equal 120. Similarly, v plus w equals 200. v minus w is 120, v plus w is 200. The difference between these is that we have minus 1w and plus 1w. So the difference between them is 2 times the wind speed is making up the difference of 80. So that means that the wind speed is 80 divided by 2, which is 40. And then if v minus w is 120 and v plus w is 200, then v, the airspeed of the Cessna, must be 160 miles per hour. This is typical of the speed, distance, time questions. So these 3 examples have really concentrated on making sure you understand what the letters represent. It's important that you think of them not just as letters, as a ballpark expression to model something, but you really have to think carefully about what is it modeling. Is it a cost? Is it a weight? Is it a number of teachers or students? And really try to understand what you are multiplying together and why, and then hopefully they all make sense. All we have to do now is find more systematic ways to solve these expressions.